back to the tutorial. So for this one, we are going to continue from the previous optical flow experiment. So I'm going to experiment with the use of optical flow in order to trigger movement of virtual object on the screen like this one. So the result will be something like this. So this is a virtual board that I can use my finger, hands, or whichever object to interact with this one. So part one of this one is the pure translation of these virtual objects, and part two we're going to do with those rotation. And then what we're going to do is to analyze how we can come up with this one. So for the composition, I put everything inside and component, and the components are at the size of the board is the radius, and also a button to initialize the working mechanism inside this, and the rest will be using optical flow from the video image, and then send in the optical flow top signal to the component. And the second input for the component will be just another TOP in order to create the texture of the virtual board objects, and then with the feedback and composition, and send back to here as the output. And for the flow, for the whole component is divided into two parts. One part is the visualization, that is 3D geometry of a ball, and then the second part is the computing the optical flow information by cropping the area where the ball is. And the two inputs, so as I mentioned, one is the optical flow TOP information, and the other will be the texture that we're going to map onto the surface of the circle. So let's work in the reverse direction. So we're going to delete everything, and then to just keep the input and output. Okay, and inside the component, I'm also going to, let me see, I also delete the component in this case. It doesn't matter, we can start from the scratch. Okay, so we now only have the input and also the output. So the first thing we're going to do is you can consider whether you would like to reduce the resolution for performance purpose, and also it may not be necessary to take the full resolution of the screen. So I usually would just keep half. So that is the thing we're going to do. And then the second thing will be like the optical flow. So the optical flow is from the palette browser in the tools that we used before, that we can search. So that is the optical flow. And then we can send in here. So the output of the optical flow is actually another TOP with the same size of the input. And then you can also see that is the 32-bit floating point with information using the red and green channel for the notation of the movement in the X and Y direction. So now we have the optical flow information ready, and the next one we're going to do is to create the component that we would like to work with. I use the same name flow booth and then go inside. So within this we have two input. One is the optical flow information, and then the second one is the texture. So we are going to work with the simple thing first, that is create the ball animation. And in order to create the ball animation, I try to recreate something a little bit simple. So we only want to do simple 2D physics, that we create a ball and with a certain radius, and the ball will be moving around on your screen by changing its position by the velocity. So the velocity comes with two components, x and y, which will be controlled by the optical information later. And we may also want to add friction or drag that slow down the velocity. And to create funny effect, that we might want to do some bouncing of the four walls of the screen. That if you consider the initial velocity of the ball is Vx and Vy, so when it hit upon the boundary, so the first thing we need to do is to have collision detection, that we detect is actually hitting on the one of the four boundaries. So in this case we use to have the size of the boundary. So in TouchDesigner, with the units dimension of the screen, that the left is minus 0.5, the right is 0.5, the top is 0.5, the bottom is minus 0.5 in x and y direction. So when it hit, for example, the bottom boundary, so the Vx, that is the horizontal component of the velocity, remain, unless you want to cater for some kind of friction that will slow it down a little bit. And otherwise the Vx component remain the same, but the Vy component will change the direction from negative to positive in this case. So the Vx would change into Vy. So when it hits upon the left and right boundary, the opposite applies. So that means the Vx change the direction, whereas the Vy remain the same. So that is the simple simulation of 2D physics in Computer Graphic 101. Okay, so we're going to implement this one in our TouchDesigner project. Okay, so let's create the ball. So that is the 2D circle. Yes. Then I also add the transform, just in case I need to make changes. And then it will go into our geometry. And then of course we have light and camera. So for camera, as usual, because it's 2D, so I choose the orthographic projection, that is the parallel projection with the origin in the center, and also the width is 1 because we are using the unit dimension. So you can see it's occupied everywhere. So it eventually will render in 2D here. And at the same time we also have material. So I use a constant material and I apply to this geometry. And we can also use the input from here as the color map for texture. So in that case we can just initially create, for example, a piece of noise in color mode and then send it to the second input as the texture like this one. And in a bit later I may also want to animate the noise to make it more interesting. So that will be the output from here. And then the second thing that I can go back here is to customize this one with a custom page. And in the custom page I have two parameter. One is the size of the circle, I call it radius, and then I add it as a floating point number. That the default one I may choose 0.05 and the maximum is 0.5, that it occupied the whole screen already. Okay, and the other one I want to add is initialize, which is supposed to initialize the virtual ball. In this case we've had the name initialize, or I can simplify with just init. Yes. So now we have two, and to capture the parameter we can just make use of the parameter chop from here. So now we have radius and init. So the radius, we can select the radius and put it into the size of our circle like this. So now we have a smaller ball. And then eventually you can send out your output, that is the moving ball, as an output parameter of this component. Okay, so the next step we're going to do is to move the ball by changing the translate parameter here. So in order to work with that one, I may want to add a number of constant that I can use it to eventually animate this virtual ball. Okay, so the first constant will be like or name as position, which come with two channels. One is TX, the other is TY. I'm going to use this to change the location of the geometry here. So in that case I can drag TX and export here, and then TY to export here. Okay, so whenever I want to do, I can move the ball around. So actually that will go from minus 0.5 to positive 0.5 in the unit dimension. So that is the position that we are going to play around with the virtual ball. And then the next thing we are going to do is to do some animation by working on this types of physics simulation of this particular ball. So that can be slightly complex, but luckily I put everything into one separate file already that we are going to copy and paste it into our script. So when I copy and paste this one, I'm going to explain what happened in these two major function. This actually is a class I define as a ball. So for this one, so we are going to play around from here. So in this case, we have a text here, and then I name it as ball, which define the class ball and also this physics simulation here. So the definition would be pretty straightforward, and I'm also going to use the numpy library. So I import here, and then we're going to define class ball here. So it comes with two functions. One is the initialize, and the other one we call update, which is the function we're going to run per every frame that we're going to change the position and probably the velocity of the moving ball. So that is the thing we're going to do. Okay, to work on with this one, we also define quite a number of other variables that I maintain in some constant chops. The first one is called the margins, which I maintain the four margins of the boundary with the left, right, bottom, and top. And then another one I call it size, which I'm going to explain a little bit later when we work with the optical flow. And then the other thing that I also keep is the position. That is the location of this particular ball is in another constant chop that I put in already with the tx and ty. So in this case, I add this one margin to define the boundary of the walls. Okay, so along with this one, I also have another constant here, which I call margin, which come with left. The left one will be minus 0.5, and then the right will be 0.5, and then the bottom will again be minus 0.5, and then last one, top, will be 0.5. That is the four boundaries of our screen. Okay, and then there will be another one called velocity, which I will replace it to now chop after we can obtain the calculation from our optical flow. So that one is velocity. So we have the x and y dimension of the velocity, which we're going to use it for moving the ball around. So okay, and then the next step we're going to do is to do some copy and paste and explanation. So I'm going to copy this into here. There's also another constant the parameter called screen. I'll explain in a while. So I copy this one and put it into this function. Okay. Okay, the tab is okay. So there's another one I call screen around here, which I use to calculate the aspect ratio. So that means the size, the ratio between the width and the height of our window. And there are multiple ways that you can obtain such information. So you can pass it from project 1 to this component, or you can directly obtain it from a parameter chop here. So for parameter chop, if you are not obtaining it from the custom, that's the one you define from the component, that you can turn off the custom, but instead you choose built-in. And then you can do a selection from here. And for this parameter, that you can also remember to go to the operator, that's the top one, the root, and also the project 1, that is the container of this particular project. And with this one you can choose W and H, which is the width and height of your project 1, that is your default screen dimension. And then you can send it to a null and then name it as screen. That I'm going to use it in here, so that is here. So with the screen, I take the channel H divided by channel W, which gives you the aspect ratio 0.5 something. And then we're going to define the four margin, that is the left, right, and top, bottom. So the left one we're going to get from the parameter called margin of that defined from here, is the operator called margins. Here, left, right, bottom, top. So the first one will be the left, and then the second one will be the right, and then the top, so bottom and top. So please note that the bottom and top, because it's in Y dimension, so by default the normalized range will be minus 0.5 to positive 0.5. But in the XY dimension of the geometry will be discounted by this aspect ratio. So that's why I need this aspect ratio to reduce the dimension of the top and bottom by around 0.5 something. So that is the two number here. And then I'm going to obtain the radius, the size of the screen, that the ball that with the channel called radius. So that one come from here. So with this select, I don't use the name select, but I can name it to radius. So in this case, I obtain the size of the radius 0.05 from the channel capital R radius. So that is the radius. And then I define two vectors. One is the position. The initial one will be 0, and then the velocity will be 0, as well. And then I also define a factor called a drag, which is kind of like friction. So imagine if you make the ball moves, and then the initial velocity come with, for example, let's say 1, and then the next frame it will be slower and slower and slower. So it's kind of like dragging factor to slow down, eventually to simulate like friction or the drag factor in real physics. So that is the use of this one. And the next one we're going to do is to compute the position by taking in the velocity and then reduce it by the dragging factor and eventually we might also need to check the bouncing of the four walls of your screen. So to save time, I will do the copy and paste again. And I will explain what happened here. Okay, it's a little bit complex. So the first thing, I also try to get the name of the operator that I define at velocity and position, that I need to change those constant. And velocity actually not change it, but I take in value from here. So the first thing we're going to do is to obtain the velocity data from the two channel X and Y from here. And then I multiply the dragging factor, which is a scalar, that 0.9 here, to the X and Y velocity, which is 2D vector. So one vector of two components, I should say, to be precise. And then the next step is to add the velocity to the position. So that means frame by frame, then the position will change by the value of the velocity, reducing 0.9 with this factor for each of the frame. And then the if else over here will be used to check the boundary. So for the position X that is 0, I need to check the left boundary, whether it is kind of hitting the boundary. If this is so, I will put the position exactly on the boundary and then reverse the direction of the velocity, that is in the X direction. Else, if it's hitting on the right boundary, that's margin 1, that is right, minus the value of the radius, and then I also put it exactly on the boundary, and then reversing the X velocity as well. And the second if else statement is handling the Y direction of the hitting the bottom and top margin and changing the vertical dimension of the velocity. Okay, and after we figure out all the position and the new velocity, and then we are going to take care of this one we haven't done yet. So that one is, if we take a look of the optical flow here, so that one we send in optical flow information. Instead of send it to a null, I send it to here. So you can see roughly the motion of myself in front of the camera. That is the red and green channel. That is the optical flow. So this whole top will be sent to here. That's the overall optical flow information. But the one we want to do is, we are not concerning the whole flow of the movement of the whole screen, but instead we only just want to focus on the circle. That is where the circle is. We would like to crop that area and then take a look at how much movement that involved in the location of the circle. So in that case, we would like to crop the optical flow information by changing the left, right, bottom and top in normalized numbers of the 4 element left, right, bottom and top. So to facilitate the program to do it automatically, I also add another constant chops with the name size, that is the size of the cropping area again with the channel called left is 0, and then right by default is 1. That's the whole area. And then I have bottom 0, and then top, which is 1. So with this one I can drag it here first in order to change it automatically in the script. So I drag it right, and then bottom and top. So in case I push the slider, actually you'll see the size of the window change according to this. So what I intend to do is to change it automatically from this script from here. So I define the size with the operator size is the size of, and then eventually I put the left, right, bottom and top here. So the calculation is I try to normalize that one, because the left is actually the position of the center of the circle minus the radius, right is plus the radius, and then the bottom is the vertical measurement of the position minus the radius, and the top is plus the radius. So with the left, right, bottom, top computed in the range of minus 0.5 to positive 0.5, I'm going to normalize it by taking in the size of the x dimension, that's 1 over here, that is 0.5 minus 0.5, that's 1 for both x and y dimension, and then use the left and right minus the left margin, bottom and top minus the bottom margin, to compute the new left, right, bottom, top in a normalized range of 0 to 1. And then the final result is I put the position 0, that is the x position, into the position of constant value 0. So the constant value 0 of the position is here. Here. So to expand this one, so the tx is constant 0 value, ty is constant 1 value over here. So eventually this update function actually will update the tx and ty here. That's the position of the ball. And at the same time, the parameter for the size here, with the constant 0, 1, 2, 3 around here, will be updated by the value of left, right, bottom and top here. So eventually it will give you the cropping area where the virtual ball is. So that is the most complex part of this program, which was compute the movement. And this one actually will not automatically do the computation, because just as a definition of the class called ball in order to work. So we also need to add another execute data here. From here you need to import this one. So we are going to from ball, which is the name of this text data, and it's actually defining the ball as well, the definition of this class. So we're going to import ball, that is the class here, and with this one we're going to define a variable called ball, and initially there's none, there's nothing here, so we are going to define global ball, and the ball will be initialized here with the class ball, and this one is the instant variable, and I make it global, that will be updated along here. So the next thing will be on every frame start. That means when we are looping each of the frame, we are going to update the ball right here with this. We're going to do the update here. So the init will be done around here when we first define the ball instance. So the next step is we need to turn on both of them. The start around here, and also the frame start we are around here. And then we need to pause this one to start. So now you see they're connected. So that means in the very beginning it will start initialize, and I'm also going to pause or to control this one by putting in the pause button from the parameter of this component, and then for every frame it will do the update section. So that is the one we would like to do. So if you would like to see something, you can also see this already updated the coupling area, which should be in the center of the screen. And then if you make, for example, like have some changes to the X dimension, or if you make some changes to the Y dimension, you also make changes to the position, and it will actually change the location of your ball with this way. So the output will be another now that you can see right here. Okay, so that is the first part. We successfully define the moving ball. So even though the movement is very minor, in this case you can see the movement here by changing the velocity. But the good thing we're going to do is we want to make use of the motion in order to obtain information. So we put in 0 to the velocity first to reset everything in the center. And then, as I mentioned, the parameter from here we also select another one called init, which is button pause here. So when we pause this one, we will initialize the ball right here. So we can connect this button back to our execution that is on start around here. So we can just click or connect this one to the pause. So whenever we press the pause button in the component, we will initialize the ball. Okay, so we can go back to have a look of the initialization. We put it back into the center of the screen. Okay, so the next step is we would like to see motion in the center of the screen right now from here. So we actually see the movement in the optical flow. And then the next step is we are going to analyze this one by having an average of all the color of the area kind of confined by the location of the ball and also the size of the ball. So we use the full image, and then we don't have a mask, so it's just give you one single pixel, and then the value of that single pixel we can obtain it through top to chop, and then we can discard the blue and alpha, just take red and green with the full image of the pixel, and then we rename it to X and Y. Now you can see the locations, the changing value of this one. You have when you move, actually you will create changes in the X and Y value, which is actually the red and green channel value, and then it will have negative and positive number depending on the direction of your movement. So the next step we're going to do is we can actually define a range such that you can ignore the very minor or subtle pixel variation, and in that case you can skip the minor movement, just take into consideration with significant movement in front of the screen. So we can do it by an expression, and this with a little bit of coding, but in this case it's not a full Python coding, but it's some kind of expression. So me.input value is the original value, and it will return, or for example, if I would like to check the range, if the range is beyond a certain value, either in the negative or positive direction, we will going to keep this value as me.input value. Otherwise, we're going to put 0 over there. So we can write an expression like the value will be me.input value if the absolute value of me.input value is greater than a number, and that number that you need to do some testing. For example, 0.001 we keep, else we put 0. So in that case we can see if I don't have any movement, it will be 0, but if I start to move, that will be the original value, or I can change the value a little bit higher to make sure that we can have some movement. So you might also want to see if you want to amplify or reduce that value by multiplying some factor. For example, if you multiply by 2, then you do double. And actually from my testing, I found that the direction is opposite, so that means I need to multiply by a negative number in order to change the direction of the movement. And if you want to, you can also see whether you would like to have a filter or this kind of spring to make some funny changes to the value. And this one will eventually go to a null, and that null we're going to replace the velocity here. So we no longer need this one, but instead we are going to use velocity here. Okay. And so we just initialize here. So now you can actually see what happened when I moving my hand across the screen. So the result will be I obtain the movement information in the cropped areas, that is the location of the board, and to analyze it to extract the red and green channel as an X and Y movement data from that particular area, and then put it as velocity. And now your original script from the update here will add the velocity information to your existing velocity. So it's something a little bit like acceleration, and then to move the board towards the positive or negative direction in both X and Y dimension, and eventually will create the movement. So we can now have a look of the result by combining the two of them. So we do an composite of the original video, and this one put on top of the video, and then send it to output. So we might also want to fine tune some of the value later, but we can just have a look of the result. So that will be something like this. It's moving pretty fast in this way. Okay, so if you consider it's moving a little bit fast, that you can enhance by changing the value by not multiplying by, or just -1, using the original speed but in opposite direction. So that will be something like this. So for the texture, actually you are free to put whatever you want over here. So the thing I have just put there is just timeline cooks with the absolute second with a max to slow it down, and then with the noise I usually try to change the Z transform, which animate the texture pattern. And if you want to, you might also want to put in like a feedback to create a trail of the motion of your moving ball. So 0.9 was a little bit too much, I reduce it to 0.5 in this case. So now we have this. So you can have fun with the pawn exercise that I adopt from the computer graphic 101 of this kind of pawn game, and then putting into TouchDesigner by using Optical Flow. So to conclude, so we have done something pretty complex in this case, which I put it inside the component right here by using the cropped area of the optical flow as a way to generate the velocity. So yes, that is the velocity here. And then with the velocity, I use it to control the location of the ball as a movement to simulate this kind of simple 2D physics. And to add more fun, you can consider to map different kind of texture, or you can animate the texture with other material. And then the remaining part we haven't done will be in the part 2 of this series to create the rotation effect. That means you can use your hand or finger to rotate the object instead of just moving it around. So that's it for this a little bit lengthy tutorial. So everything will be in the Patreon in a moment that I put in the Python script, the component, and also the video will come very soon. So until the next one, happy coding in TouchDesigner. Bye bye.